Jai Hind. The today topic which we are going to discuss today is concurrency control in transactions. Basically, here we are going to discuss concurrency with respect to the transactions in DBMS. So first, the introduction of concurrency control, that is basically what is concurrency. Concurrency is nothing when two or more transactions are executing parallelly and they are also sharing the same data items or working on the same record set, then we say they are executing concurrently. And once they are working on some shared data, then this implies that the consistency of that data should remain same throughout the life cycle of your transactions. So, what is concurrency control? It is the management of concurrent transaction execution. That is, the transactions they are executing concurrently, but due to their concurrent execution, the consistency of data should remain proper. So, DBMS implement concurrency control techniques to ensure serializability and isolation of transaction in order to guard the consistency and integrity of the database. That is, your concurrency control manager, it is working on two asset property. One is your consistency and another one is your integrity. Concurrency control can be performed by the DBMS with various methods. We are having several methods, out of which currently we are going to discuss locking method, time stamping method, and other are your optimistic method, which we are going to discuss in other lecture. But in optimistic methods, we are having multiple granularity scheme, multi-version schemes, and so on. So first protocol which we are going to discuss for the concurrent execution of the transaction is the lock based protocol. So it is the most commonly used technique and it works on the concept of locking the data item. That is, whatever data item you are sharing, you are working, whether you are performing the read operation or the write operation, you need to lock it first. So, a lock on a data item, it specifies the status of the item with respect to possible operations like read and write that can be applied to it. If a transaction T wants to modify a data item Q, let's say the data item is our Q. So, a lock must be associated with the Q. If any other transaction, for example T2, already working on this data item, that is Q, then no doubtly your T1 has to wait until T2 releases the lock on your data item Q. If there is no other transaction working on that particular data item Q, then automatically T1 lock the data item, that is your Q. And later on, if some other transaction is coming in the system, let's suppose T3, T4, and it wants to work on data item Q, then they put on withheld by your concurrency control manager. They have to wait until T1 complete its execution and it release the lock on data item Q. When we are talking about the locks, we are having two modes, that is, the data item Q can be logged on two ways. One is your exclusive mode and another one is your shared mode. Now, what the exclusive mode says is, it says that once you are locking the data item Q, here we have specified it with the help of X. So, if you are working on a data item X and you have logged it with the help of a exclusive lock, then you can perform both the operation on it, that is read as well as write operation. Whereas, if you have put the lock shared mode on your data item X, then you are able to perform only one operation, that is the read operation. And how we are denoting these locks? Exclusive lock is denoted with the help of lock X. Shared mode is denoted with the help of lock S. Lock requests are made to concurrency control manager. That is, whenever you are requesting a data item, you have to lock it. And where your lock request is going? It is going to the concurrency control manager. So the transaction can proceed only after the request is fulfilled. That is, suppose you have requested for the exclusive mode, then until and unless you get a exclusive mode lock on your data item, you are not allowed to proceed further. This is our lock compatibility matrix. We are having two modes. One is shared and another one is your exclusive. What the lock compatibility matrix saying? It is saying that is, if you are, let's suppose if you are having lock S, then and there's a T1 transaction who is having lock S. Now T2 transaction come into the system and it demanded lock S. Then according to this compatibility matrix, it would be given immediately, and the transaction T2, it don't need to wait. But what if T2 demand for X? Now according to this compatibility matrix, T1 is already having lock S on the data item Q, and T2, it is requesting lock X on the data item Q. Then according to this matrix, it is saying false. So it has to, transaction T2 has to wait. Similarly, if T1 is having lock X, then according to this matrix, any other transaction which is coming into the system, and if it is demanding lock S or X, then none would be granted. And this we have already seen in the conflict serializability. It's what in the previous lecture, what it says? It says that if we are working in the read mode and another transaction is coming into the system and it is also wants to read that data item, then we say it is a non-conflicting instruction and it can go. We fulfill the request. But what if the transaction is working on write mode and some other transaction is coming in the read or the write mode? Then we automatically we say, okay, this is the conflicting instructions, and here we don't swap the things or we don't grant the request. So same concept is here. A transaction may be granted a lock on an item if the requested lock is compatible with the locks already held on the item by other transaction. This I had already shown with the help of an example. Any number of transactions can hold shared locks, but if any transaction holds an exclusive lock on the item, then no other transaction may hold any kind of lock, that is S or X. This is what your compatibility matrix says. If a lock cannot be granted, then the requesting transaction is made to wait till all the incompatible locks held by other transactions have been released. The lock is then granted. That is, if T1 is working on X and T2 comes for X, then it has to wait, and up to what time it has to wait? Until T1 releases this locks. As soon as T1 releases its lock, T2 would be granted permission and it will come out of the waiting state. If a lock cannot be granted, the requesting transaction is made to wait till all the incompatible locks held by other transactions have been released. This already we have discussed. So this is simple example where we are seeing that how the locking or unlocking is being done. Here what happened, we have first requested in the shared mode on the data item A, then we perform the reading operation, then we have unlocked it. Similarly, we are locking it on shared mode, only read operation is permissible. Now here if you want to write on B, then this won't happen until and unless this lock is your exclusive mode lock. You unlock it. Now what is happening here? You are storing A in buffer. Here, here again you are storing the things in buffer, and here you are doing the calculation on your buffer, not on the database. Locking as above is not sufficient to guarantee the serializability. Now, if you look at this particular example, very simple to follow. But when multiple transactions they are executing concurrently with this transaction, then it becomes quite complex. Why it becomes complex? Let's suppose if A and B get updated in between the read of A and B, then the displayed sum would be wrong in this case. So, a locking protocol is a set of rules followed by all transactions while requesting and releasing the locks. Why we are going for the lock based protocols? A simple scenario. Here we are having two transactions, T3 and T4. Let's suppose T3 has put the lock in the exclusive mode. Here we are reading, and here we have done the updation, and here we are writing it back. So here lock S, clear, it is reading A, and here we are having it need lock SB. So it is working on data item B, logged. It is first working on data item A, locked, and it is demanding a lock on B, so it has to wait. Similarly, now it demands for lock X on which data item? A. So again A is held by, lock on A is held by transaction T4, so it needs to wait. Now, if you look at this simple scenario, both the transactions, that is T3 and T4, they are waiting for one another to release the locks. But since their work is depending on one another, so in this case, what is happening? None is executing further, and this is the scenario of deadlock. So, to avoid starvation of transactions by granting the locks, we use two-phase locking protocol. To avoid such kind of situations, we are using a locking protocol which is known by the name two-phase locking protocol. It is working on two phases. The very first phase is the growing phase, and then this phase 2 is your shrinking phase. What is the growing phase? In this phase, we obtain all the locks on the data items on which the transaction needs. Once this transaction is in the growing phase, then no locks would be released. Clear? So, what we are having, suppose T1 wants to work on data items Q, P, B, and let's suppose X. Now, what is happening? It need to lock them. But here, if it wants to unlock, let's suppose it is requesting for Q, it has sent the request for Q, granted. It sends for a lock request for on data item B, granted. But then it tries to unlock Q, then it won't be fulfilled. Why? Because still it need to send the request for locking on data item X. Similarly, in phase 2, what is happening? We are releasing all the locks. And once you are in the shrinking phase, then you cannot obtain the locks in this phase. And this protocol, it ensures conflict serializable schedules. That is the schedules which we are getting with the help of two-phase locking protocol, although all those schedules, they are conflict serializable. So, two-phase locking does not ensure freedom from deadlock, but this is the disadvantage as we have seen earlier. Cascading rollback is possible under two-phase locking protocol. What is cascading rollback? That is, suppose T1 is working, then we are having T2 is working, we are having T3 is working, and look, suppose T3 some problem come up. So, it starts rolling back. Now T2 is rolling back and T3 is also rolling back. But originally who rolled back? T3. But the if impact is found on T2 also. Similarly, maybe T1, the impact of T2 is on T1 and T1 also starts rolling back. So this is your cascading rolling back, and such kind of situations is possible in the case of two-phase rolling protocol. And to avoid this, we are having a modified version, strict two-phase locking protocol. Here a transaction must hold all its exclusive lock till it's committed or abort. That is, before releasing the locks, that is, and before going to the shrinking phase, the transaction must issue either commit or abort protocol command. How we implement a lock? A lock manager can be implemented as a separate process to which transactions set lock and unlock request. The lock manager replies to a lock request by sending a lock grant message, that is, the lock has been granted, or a message asking the transaction to roll back in case of deadlock. The requesting transaction wait until its request is answered. The lock manager maintains a data structure called a lock table. That is, lock manager, it is maintaining a data structure by a name lock table, which records all the granted locks and pending request. The lock table is usually implemented as an in-memory hash table indexed on the name of the data item be logged. So this is a simple hash table, and if you look at this hash table, we are having multiple values, and these values, they are corresponding to the transactions on a particular data set, data item. Here the black is a rectangle is showing that we have granted the lock to that particular transaction, and the white is indicating the waiting request. Lock table also record the type of lock granted or requested, that is, or what kind of exclusive mode or shared mode. All these information is stored in this hash table. No request is added to the end of the queue, to the end of the queue of request for the data item and granted if it is compatible with all the earlier locks. Unlock requests result in the request being deleted, and the later requests are checked to see if they can now be granted. That is, if new entry is coming, then we are adding it to the end of the queue. If transaction abort, then all the waiting or the granted request of the transaction are deleted. Suppose here we are having a transaction T8 and it got aborted. So here we release the lock. Again here T8 is working on some data item. Again that particular lock is released over there also. So the lock manager may keep a list of locks held by each transaction to implement this efficiently. Another set of concurrency control protocol is your graph-based protocols. Here, these protocols are an alternative to two-phase locking protocol. Here, we impose a partial ordering on the set D. We are having a set D, which comprises of the unit D1, D2 to DH of all the data items. These are my data items. And if DI to DJ, that is, we are inserting, these are my set of vertices, data items, and we are inserting an edge from DI to DJ. Any transaction assessing both DI and DJ must access the data DI before accessing the data DJ. That it says, if transaction is using these two data items, then first it will use the data item I, and only then it would be able to use the data item J. Implies that the data set D may now be viewed as a directed acyclic graph called a database graph. Here the graph is known by the name database graph, and here we are having a simple version and the most popular version of the database graph, that is a tree protocol. Here we are having a tree, using a tree data structure, and these are my data items. only exclusive locks are allowed. That is what kind of locks we are working on the tree protocol. It is my exclusive locks. The first lock by TI may be on any data item. That is, let's suppose transaction TI wants to lock data item E, then it can do so. Subsequently, a data item Q can be locked by TI only if the parent of Q is locked. That is, here you have locked the E, but now you want to lock B, then this is not possible. That is, before locking E, you need to lock the parent B. Clear? But if you are on this and you want to lock any child of E, then you can do so. Data items may be unlocked at any time. That is, it is not following any growing or shrinking phase. That is, you can lock and unlock the data items at any point. The data item that has been locked and unlocked by TI cannot subsequently be relocked by TI, and this is imposing a issue or a challenge or a limitation in the tree protocol. That is, suppose it is working on IE, it locked it and then it unlocked it, but again it wants to lock it later on, then the permission is not granted. Another limitation in this case is that suppose you are working on this data item, then and you want to use this data item later on, then unnecessarily you have to lock D also. So if another transaction it wants to operate on D, then it can D only, then it is told to wait until and unless the earlier transaction release its lock on D. So unnecessarily what is happening, your concurrency on of the transaction, that is the number of transactions executing concurrently, it got reduced. When you are using tree protocol, it ensures conflict serializability as well as important thing that it is free from the deadlock. Your 2PC protocol, we are having deadlocks over there, but in the case of the tree protocol, it is free from the deadlock. Unlocking may occur earlier in the tree locking protocol. What is happening in the 2PC? You are growing and then shrinking. But in the case of the tree protocol, we have given the freedom. Shorter waiting times are due to this and concurrency increases. Protocol is deadlock free, and since it is deadlock free, so no rollback is required. But what is the problem? It does not guarantee the recoverability or the cascade freedom. Need to introduce commit dependencies to ensure the recoverability. Also, transactions may have to lock the data items that they are not using. Earlier, we have shown with the help of example. Here, I am not using data item D, but still I need to lock it. So due to this, locking overhead is increasing, additional waiting time is increasing, and it is leading to low concurrency concurrency output. This is another set of protocol, that is my time stamp based protocol. Here what we are using, we are assigning time stamp value to my transaction as well as to my read and write operation. Here the time stamp is assigned by the database system before the transaction TI it starts execution. If a transaction TI has been assigned timestamp TI and a new transaction TJ enters, automatically the timestamp value of TJ it should be larger than the timestamp value of TI. And how we are ensuring it? Either we are using the system clock to implement the timestamp value, or we are using a logical counter. So with the help of these two algorithms, we are able to assign the timestamp value to transactions TI and TJ. Each transaction is issued a timestamp when it enters the system. If an old transaction TI has a stamp TI and a new transaction TJ is assigned timestamp TJ, then automatically the timestamp of TI is less than timestamp of TJ. The protocol manages concurrent execution such that the timestamp determine this, and how the serializability order has been achieved with the help of these timestamp value. In order to assure the serializability behavior, the protocol maintains for each data item, that is TS is corresponding to each transaction, but W timestamp and R timestamp, it corresponds to each data value. It is the largest timestamp of any transaction that executed write queue successfully. For example, T1 has come and T2 has come. It issues the write operation at the time 10:05, and T2 it issues the write operation at 10:10. So what is happening? It also executed successfully. But what is the W timestamp value? It is going to be this. And the same rule goes with the R timestamp. It is the largest timestamp of any transaction that executed read queue successfully. The timestamp ordering protocol ensures that any conflicting read and write operations are executed in timestamp order. That is, all your conflicting instructions, they should be executed in the timestamp order. Suppose a transaction Ti issues a read queue. Suppose a transaction Ti comes and it wants to read the data item Q. Then these two conditions need to be checked. And with what value we are checking? We are checking with the value W. Here, if timestamp of Ti is less than or equal to write timestamp of Q, then Ti needs to read a value of Q that was already overwritten. Clearly, so here in this case, what is happening? Read operation is rejected and Ti need to be rolled back. But if timestamp value of Ti is greater than your W timestamp of Q, then the read operation is executed in this case, and R timestamp value is reset to the maximum of read timestamp Q or TS of Ti. Similarly, we need to check before executing this operation, and what we need to check? We need to check with the R timestamp of Q as well as W timestamp of Q. So first we are making a comparison with read timestamp value. If timestamp of Ti is less than read timestamp of Q, then what is happening? Then the value of Q that Ti is producing was needed previously, and the system assumed that the value would never be produced. Hence, what need to be done? Write operation is rejected and Ti need to be rolled back. But if now we are comparing the TS value with the write timestamp. Here Ti is attempting to write an obsolete value of Q, and hence write operation is rejected. Otherwise, the write operation is executed and write timestamp Q is set to TS of Ti. That is, whichever transaction is executing the write operation, your W timestamp is set to that particular value. This is a particular schedule for the several data items for the transactions with the timestamps 1, 2, 3, 4 and 5. So here, let's suppose here T5, here the read value, its timestamp value is 5. At this time, no is so its timestamp value is set to 5. Now T2 comes, here it's set to, on the data item Y, the R timestamp value on Y, it is set to 2. Again T1 comes. Now according to my read operation, what is happening? What need to check? With the R, with the W, read operation, and here what we are doing, we are again performing the read, so no need to check, the permission is granted. But here when we are coming on the write Y, so this is the data item with we want to perform the operation write. So here we goes according to this write Q. Clear? We need to compare with the R timestamp value of Y. So what is the R timestamp value of Y in this case? In this case, this is 1, this is 2, it is going to be 2. we need to keep the maximum value. So it is 2. And here we are having 3. So according to this particular, what is happening here, the TSTI is less than R. So 3 is greater than 2. So this rule is not happening. So here we will go and the write operation is permitted. This is how we go with the things. This is another this is another schedule. We are having read operation, then we are performing the write and the write. Let's see in this case. So once we are performing the read, let's suppose its timestamp value is 16 and its timestamp value is 17. So here R value is going to be 16. Now T17 comes and it performs the write Q operation. So what is happening? According to my rule, I need to perform the write operation, and earlier we are having the R value. So here what we need to check, we go according, and the TS of TI, it is 17 and the R timestamp value on my Q data item, it is 16. So in this case, the write permission is granted. But what is happening here? Once it wants to write the data item Q, so here it is my 17 value, and here I am having T16. So what is happening? According to my this policy, the 16 is less than 17. So again it is not allowed. It need to wait. So this is all about the concurrency control protocol. So we have discussed your log based protocol, graph based protocol, and then we have discussed the timestamp protocols. These are the references which I refer while preparing the slides. Thank you.